So we're going to open the session. I would like to say that the government of Aragon, as a response of a demand of all the parliamentary group, has created the paper on the management of waste, contaminant waste in Aragon, which includes several decontamination actions and an important development of infrastructures and follow-up that can influence contaminants. In our session, the speakers are going to present some of these actions. Firstly, we will give the floor to Mrs. Elena Cano, who is the Chief of Service of the Contaminant Soils Department, my boss, in fact. She's been working for the last 2 years as the responsible person for this. And she's going to present a case study on the influence of geology and the presence of different matrices on the applicability of HCH remediation technologies. Thank you very much, Jesus. With this presentation, I intend to decontextualize the geology of all the, to give a context of all the presentations that you're going to hear and see later on. First of all, I'm talking about the problem that you know already in the Incinosa factory, the one you see on the left-hand side. It produced lindane between 1975 and 1989 in the municipality of Sabiñanigo. As you know, per ton of lindane produced, between 8 and 10 tons of other HCH isomers were being produced. They were waste, they didn't have any commercial value, and therefore they were dumped in landfills. In the case of Incinosa, it was the waste was taken to 2 sites. Between 1975 and 1983, Incinosa used the SARDAS landfill, which was also the dumping site or the dump of all municipal waste, and the chemical industry site for the waste of all this industry. Right, and between 1984 and 1992, as the Sardas landfill was filled up, the Bailín landfill was used, which belonged to the Incinosa factory, and it contains residues, HCH waste, and the soils are contaminated by HCH. But Incinosa did not only produce solid waste and these non-commercial isomers of HCH with the lindane production, there were also liquid waste produced as the result of photochlorination processes and the distillation tails in the fractioned distillation phase or process of the HCH. In total, between the 2 landfills, we have around 120,000 tons of solid waste and between 40 and 50 tons that were that are liquid waste and that we can find in as a dense phase or liquid phase. Here you can see the discharge site, and you see that there is a national road passing by that was built in 1985, which was cutting the dump by half. And so the waste went to the lower part of the layers, around 50,000 cubic meters. And as for Bailín, that is regarding Sardas. And as for Bailín, in 2014, the government of Aragon transferred all this waste to a new safety landfill specialized special for hazardous waste. Why? Because those were the years when, when the dumps on the landfills were in operation, according to the dangerous materials regulation. None of these landfills were waterproof. And here you can see the Gallego River, which is close to the 3 sites. Encinosa is at the right-hand side. Sardas is the well, at the north there is a Sardas dump, and at the south there is the Bailin dump or landfill. These are relatively close to one another. However, the geological characteristics of the area, the different layers, matrices, contamination matrices that we have, and the different contaminant phases, the liquid and solid phases, make it necessary to apply a wide range of remediation solutions in all these matrices or matrices. Well, let's know more about the geological context. The three sites are close to Spain, near the Pyrenees mountains, and they are therefore influenced by the formation structures of the Pyrenees. The Pyrenees were formed by the clash against the Iberian plate and the European plate. They were initially separated by the sea, but then as the Pyrenees were being formed, the two plates were growing closer, and the Pyrenean furrow or groove was being filled up with different marls, for example, and other materials such as sandstones and different types of deposits. Here you can see a series of wrinkles or folds rather than wrinkles, folds, creases. And in these sites, we have the Basa anticline. And in the axis of this anticline, you can see the axis. And you can see the Basa anticline in some vertical strata of siltstones and sandstones. This is the geological plan of the map. I'm not going to get into detail. And we are going to see some didactic images on the materials of the area. This is a drawn overview of the sites. This is Encinosa. In front, we have the Sardas landfill, and Bailin would be a little bit outside the photograph, but aligned with this relief. You see the Gallego River and the Sabiñanigo Dam between Sardas and Encinosa, and the base, the soil would be the marls. And here you can see the Pyrenees structures according to the anticline axis, and you see the materials with the outcrop of the ocean groove. And in Sardas, you can find alluvial materials, those coming from different eras, like geoglacial materials and glacier metric, and even wider than 1 meter glacier materials, as well as marls, as we were saying. And we can find also some sandstone and silts, which are softer sediments that also present some complexities when implementing the solutions. Let's see side by side. This is the Encinosa factory. We have the marls here on the subsoil and as the basic or foundations of all these. Then they are highly fractured, then they are altered. They have more permeability than the healthy marls that are at the deeper layers. And on top, you have the alluvial materials. In the upper part, you see that the Encinosa factory is divided into two different platforms, a higher and a lower platform. In the higher platform, we find these fluvio-glacial materials, and between this and the lower platform, the alluvial of sandstone. And the phreatic level would coincide with the altered marls, but this is highly variable according to rainfall. so that sometimes it is within the alluvial layer. We have the relief, the terrain where the site soil is. And for a certain time of the operation, this was not paved. And therefore, this soil was polluted, was contaminated, sorry, and then it was paved. And some walls of the buildings, the ones associated to the production walls or sites of the factory, are also contaminated up to a certain extent. In two different points of in the higher layer and in the lower layer associated to some waste deposits, we have a dense phase, so DNAPL. Now you see the SARDAS landfill. You see the higher part of the dump and the inferior part where these materials were deposited. Here you have the Sabiñanigo Dam, the Gallego River here. Well, dam is not really a dam, it's a reservoir rather. And you see the colluvium, the landfill, the anthropic fill. Rather than a reservoir, we could say that it is a tailing pond. And so you have 12 minutes left. In the lower part, we have the healthy marls, on top the weathered marls. Then we have the sandy gravels and the silts at the phreatic level. This reservoir is really a hydroelectric reservoir, and therefore it has ups and downs along each day with a kind of tide as a result. And then we have DNAPL both in the discharge main body and in some of the marl fractures under the road and in the lower part where there was the tailing pond. This DNAPL has been extended to the silts, and therefore it is rather difficult to extract because they are very permeable, and to the alluvial part up to the basis of, or the base of the weathered marls. Here we have the Bailín landfill. The Gallego River would be at 800 meters away, and up to 2014 we were having the solid HCH landfill, and in 2014 we transferred this waste to the new landfill. What is the geology that we find here? A series of sandstone materials. These are all subvertical strata and alternance of sandstones and siltstones. The sandstones are more yellowish and the siltstones are reddish. These fractures are fractured up to 50 meters depth, and the phreatic level is around the sandstone layer or level, and there is a transversal flow of water. In the sandstones, we have the DNAPL that we saw in the live surfing. We have it as a residue or in a residual way. And the surface of the landfill is having a certain level of contamination due to the leachates that were filtered when operating on the landfill. You see here some runoff basins that gather or collect all the runoff of these areas and the treatment areas. I'm finishing. What kind of matrices do we find here? The pure waste. We also have free DNAPL in SARDAS and at the basis of the marls as something that is remaining in Bailín, but not a lot. We have residual DNAPL in baleen and not pumpable DNAPL in the SARDAS landfill, some water contaminated by the contamination plume, leachates and sludges, which is what we pump in the control boreholes, and the contaminated materials that are accumulated. We have absorbed DNAPL in the Vadose zone and granular DNAPL in the runoff deposits or the runoff basins or ponds. This is a summary of all the different matrices. We have also dissolved HCH in the groundwater. I forgot to mention that. And the conclusion is that in order to treat every one of these matrices, we need to apply up to 12 different technologies. We apply many of them systematically. Others are under research and some of them are under the pilot phase. In any case, we need to continue the typical treatment with physical, chemical treatment and biological treatment. Most of these treatments are going to be explained in the other presentations. So thank you very much for your attention. I'm finishing my presentation here. Thank you.
Good afternoon. My name is Sonia Velilla. I am technical assistant and mining engineer of the Service of Contaminated Soils of the Government of Aragon, and I will be talking about unique strategic projects in the sites affected by HCH in Aragon. These projects are within the map, the route map of the strategic plan of decontamination of the sites associated to Lindain in Aragon. Outside in the exhibit hall, we have left some of the copies of this strategic plan. Also in our website, you will find our strategic plan. I will be talking about 3 particular projects. As I said, they are within the route map of the strategic plan, action plan. The first is the definite final closure of the site, and the other 2 will be within action number 3. The definite closure of the baleen security cell right now. Well, here you can see the background of this security cell action. The last one was in 2014, moving the waste to the old landfill to the security cell, and then there was a sealing, a provisional sealing with a PA film, with the idea that they were going to be received. It was going to be received more waste from other landfills. This provisional closure is now 9 years old, and now we are on stage number 3 for the definite closure. Here we can see some images of the old landfill with the waste. Also works in the security cell, and here we can see an overview of the situation. As I said, right now there's a temporary sealing, and then the current situation is that this temporary sealing is 9 years old. This PS film exposed to the climatology for which it was not designed. So in 2021, it did undergo a quality check, and the results were acceptable. The security cell was designed to host both waste from the Baling old landfill and other waste coming from other sites. Right now, it is up to 50% of its capacity. Particularly, the waste that were thought to be or planned to be moved there over the past 9 years, we decided to change this plan. The waste inside the old Inquinosa factory had been managed externally over the past 2 years, and waste from the future dismantling of the factory, I will later on explain what the treatment will be applied. Also, we foresaw to have waste from the cleaning, baling, ravine, and from other auxiliary facilities. Right now, the project only foresees to have 1,232 cubic meters. This waste will be stored in the red area here. In the execution of the works, we foresee to spend 2 weeks. We chose this section because of the security conditions it offers. Here we can see each of the phases of the project, and we have planned for it to have a duration of 6 months with over 2,700,000. And then I will be talking about one particular part of the strategic project, which is the hydrological correction of the north zone of the old Bailing landfill. We will be having 2 accesses in the north area that will be refilled with technosoils we are still studying. And in these areas, we are aiming to minimize dragging produced by runoff, also bioremediating the superficial zone of the surface and bed of zone, and ability to retain and degrade contaminants. Here we can see the traces of the main vials. And when we thought about this project, we took into account certain alternatives for the walls. We finally decided to have gabion walls because we thought they were the most advantageous. Here we see the profiles for the road type and terrace type, and this will mean 5 months for the vials and another 4 months and a half for the terraces, with a budget of over 1 million euros. As said before, we are right now testing the type of technosoils and what will be the solution for the actual materials, so that we are applying a circular mindset to this. Here you can see some pictures of the different tests and trials. We even planted some tomato plants to check. And very quickly, I will talk about the dismantling and demolition of the old Inquinosa facility, which is one of the other unique projects in our portfolio. Right now, this facility is an industrial derelict area. Before this project, a characterization of contaminants has been carried out, both on soil and water and air. Particularly in subterranean water, we are over the reference values, whereas in air and particulated matter, we are below these levels. We also carried out a characterization of the contamination wall in the walls in 2018. And with the sampling and the analysis, we concluded that most of the contaminant load was in the paintings and in the covering of the plaster of the walls. We did a design of the project in a very modular way. Depending on this planification, we will be able to execute each section, also depending on the funding. We are combining several techniques to avoid dispersion of contamination. We have thought of a previous or a prior stage for the for containing all the contamination, and then 3 stages for the dismantling phase. This will go from the lower level to the higher level of contamination. So we will start with the facilities themselves, then the auxiliary buildings, and we will end up with the process buildings, which show the highest levels of contamination. Here we can see the volume of debris that will be generated with the dismantling, and in order to compare, there will be a movement or 0.001 ton a day, which compared to the dismantling of the old Bailing landfill, you very clearly see the difference in movement. Here we can see the different techniques to be used during the dismantling. It will be practically manual dismantling, applying oxidative painting technique, horizontal shot blasting, and then a block removal of approximately 40 per 40 centimeters to avoid dispersion. We will apply certain preventive and corrective measures to avoid dispersion of dust, to avoid also discharges of groundwater, and to protect the health of the workers. We also established certain stop thresholds based on the historic of air quality that our colleagues will be talking about later on in more detail, and we established stop thresholds below reference values. The complete execution of this project will be around 17 months with a cost of over 4 million euros approximately. As a breaking news, last Friday we received the report from the Environmental Agency, and it was favorable. To summarize, in order to execute these 3 projects, we need a rain of money adding up to over 8 million euros. If you have anything to contribute with, we will put a box outside so you can leave some money. Anyway, thank you very much to Laura Monge and Adrian Visanzay, who had been the chief editors of the project, together with the whole team of SARGA. Thank you very much. And now Joaquín Guadaño, who is the chief of projects in Ingrisa. It's a public company responsible for the monitoring and follow-up of the SARDAS landfill. He will be talking about the multidisciplinary perspective of the environmental management of the SARDAS site. Okay, so a multidisciplinary perspective of the environmental management of the SARDAS sites might sound too much, but in the end we will be talking about this. I want to introduce our work team in SARDAS. You will be seeing them all along these days. And I would like to summarize the concept model of the site and to summarize what we do in these 10 minutes. That's the time I have today. Here you can see our work team, or most of them. We meet every year to share all the progress and news. The last two meetings were in person. Most of you are also here. So these are the meetings on the site itself. Who work in the SARDAS site? Well, apart from the government of Aragon coordinating our work, and SARGA, who support us with all the analysis, we also have a big group of university research teams, like the Complutense University with Aurora Santos supporting us with physical, chemical remediation, oxidant, etc. Also the University of A Coruña with Javier Samper's team supporting us with the mathematical modelization or modeling, like entries and outputs of water. The University of Castilla-La Mancha in charge, in this case, of the fields. They support us with their electroremediation, and the Autonomous University of Barcelona supporting us with the techniques of biological remediation, and the Technical University of Madrid has been supporting us with the characterization of the physical features, and then the IMIDRA, the Agro Investigation Institution of Madrid, supporting us with the study of the refill materials. And as for the team itself, you will be getting to know them along the Congress. Here you can see the SARDAS site. This picture shows the whole site. As you can see, an image is worth 1,000 words. You can see here the landfill, the different ponds of leachates, and the treatment plant. I'd like you to focus on this line representing certain profiles that you will be seeing later on, profiles of the soil, of the terrain. I just would like to show you about the history of this site and why we got where we are. So there are 6 profiles representing different moments. The first up left is the site before the Sabiñanigo lake or reservoir. So we have the aquifer, normal, free, conventional aquifer with some fields above. And then in the 60s, the reservoir was built, and that meant the levels, of course, would grow. So it was a confined aquifer with associated loss of quality of the soil and also the fields. In the 70s, the landfill was operational with the deposit of waste. We have seen that's the source of the main issue, with the free phase represented with this red line that was progressing more and more. In the 80s, the landfill is full. And it is from then on that the Bailin landfill started to be used. In the 1990s, this road was constructed. This is important because there was a modification in the geometry of the landfill, and part of the soil was deposited at the foot of the landfill. And in the 1990s, the landfill was sealed. I would like to highlight mainly that despite the fact that today we see the site as it is here, more or less isolated, to be honest. Oh, sorry, this is not running correctly. The truth is that this is not a contaminant mass that's inside the landfill and is being filtered slowly. No. The question is that it is not a contaminant mass and is isolated and is being filtered or leaking. The thing is that in 1995, the situation was more or less the same as today. So there was this screen built, but then most of the affection or the impact was left outside. Now I would like to show you what we do. I will divide this into the characterization techniques and decontamination techniques. That's mainly what we do. So as you can see here in characterization techniques, we have worked with the most typical ones, such as borehole drilling, or radon emanometry, and other techniques, geophysical techniques, due to the topography, many different reasons. I will show you some examples so that you see what we do. About the vertical borehole drilling, it looks as if it is the most simple technique, but as you can see here, depending on the areas, here you can see the scene we put up, so that we work with the water that is coming up from the soil. We also do inclined or diagonal borehole drilling. Also, we had to take this altitude photography. It's not working. Maybe I need to be closer to the computer. It's not really working. Also, in this slide, you can see an injection of surfactant and with some electrical tomographies. So you can see very clearly the injection and the direction it's taking. We also have sensors, tens of sensors all over the site, measuring since 2014 the levels in the reservoir, also temperature in the aquifer of the reservoir, etc. So hordes of data. Also with biological techniques, we make samplings of plants, identification of microorganisms, counting of bacteria. Excuse me, this is working really, really weird. Here, I wanted to show you our work together with the Autonomous University of Barcelona. You can see here the huge number of microcosmos, so that we can study the microbiological life in the aquifer. And then we are also doing some characterization of the bacterial communities to know which of them have the best activity to be used in remediation tasks. So this is a picture of one of the samplings in the leachates ponds. So these show what was the highest level of degradation. Now, more examples of characterization of bacteria and about remediation techniques. You see, we have tried many of them, from thermal desorption. This is a plant in Cadiz in the south of Spain. And As you well know, desorption is very efficient. We also did some tests with nanoscale zero-valent iron. We also did biopiles with 400 tons of treatment. Biobatteries. We are also working on surfactant enhanced aquifer remediation. You see more or less the area we are acting in the alluvial aquifer. And here you can see some pictures of the treatment with surfactants and the free phase is where we work with. And we can see with these decanting or clarification with the drops, we can study the composition of these drops. And with the University of Castilla-La Mancha, we are working on this technique, electrokinetic techniques. We recreated the limes, so the silts, sorry, of the site. And here some small scale models, and we also carried out these multidisciplinary management. I just wanted to give you an example. We did a tracer test, and I say multidisciplinary because we received support from the La Coruña University and the chemists from the University of Complutense University, also Sarga with the previous analytics, and the Complutense University with the post-analysis. And we were not very sure about velocity of water because of the low flow. It took us 15 days to reach the peak. The control borehole was 4 meters deep. And I say multidisciplinary because all these tests give us data so that with the physicochemical techniques, we are more able to know the velocity of water. And for models, it is really, really key in order to calibrate models with real values. And also for bioremediation, it is also very important because we know that any oxygen injection, anything that we do, we now know the velocity, the speed it will be working with. Okay, this is off again. Sorry. I think this was the last one. Yes, yes, it is. I just wanted to introduce you our work on the site and our team. And they will be talking about some of the things I show you here.
I'm going to introduce you to Laura Monge. She is an engineer and she has been working for a couple of years with us. And she's going to speak about the purification, treatment, and analysis or analytics service or department. Okay, this is what we call the horizontal task because it encompasses a series of tasks that are purification, analysis, and laboratory management service. And this is a technical service that we provide to the government of Aragon. It is a horizontal task, as I said, encompassing all these tasks. Before anything else, I would like to say that Sarga is an instrumental company of the region of Aragon, and this is how it appears here. It is at the service of contaminated soils, of the climate change and environmental education of the government of Aragon. This is a little summary of the large activities that we're tackling in this area. The large blocks are the environmental monitoring. I'm sorry. Maintenance, operation, and management of the different infrastructures, such as treatment plant, laboratories, and other ancillary structures in the sites. The support, the technical assistance through the wording of reports. And a new line that we are supporting increasingly is the tests and research, where we are supporting the different entities on the field and in the development of analysis, everything under the umbrella of safety and in coordination with other departments. The origin of the problem is the lindane production in the Inquinosa factory, which produced a series of waste that was dumped in different sites in the municipality of Sabiñanigo. That is the Sargas and Bailin landfills. As you can see on the right-hand photograph, they are very close to the Gallego riverbed, and this entails a very complex environmental issue. Maybe I would say the most important environmental problem that we have here in Spain currently. Within the tasks of the environmental follow-up, there is the control of water quality, which is not only the monitoring protocol of Gallego River, but we also make follow-up of the water quality, follow-up of leachates and runoff that may go through the HCH affected sites. The monitoring or surveillance protocol is a tool that is really serving us as an early warning mechanism that ensures that all the different public administrations involved in the monitoring of the hydrogeological system, we can give an answer, an early answer or response, sorry, to a contamination event. The government of Aragon and Sarga Muestrea has along 150 kilometers of the Gallego River, different gauges, taking samples that are analyzed every day, giving a very quick and agile response to have the transparency on the current state of the waters or water bodies. Apart from water quality, we also monitor the air quality near the sites. We have a network of monitoring locations, 11 specifically, where we monitor the air quality, the gas quality, these gases in sedimentable particles, and the particles or particulate particles in the air. These are pictures of different positions that we have, the 11 positions. Well, the salad bowl, wink, wink to Maria Angeles, this is a private joke, and the different gauges and the continuous laser gauges that we have located in the Inquinosa factory, because there are some works being carried out at this moment. Another matrix is the soil matrix. Apart from the points associated to the air monitoring network, which are fixed points, we also conduct sampling and analysis of quality in those soils that come from sites that might be affected by the HCH discharges, or those sites where it is necessary to make this follow-up or this monitoring of the soil quality. Another important aspect that we, Sarga, conduct every year is an ecological assessment of the riverbed through biological and hydromorphological indicators, we analyze the quality of the water at the riverbed once a year at least. One aspect that I would like to mention is that from 2020, we implemented this study with an analysis of the population, bird population status as well. Another big block of this project is the exploitation, maintenance, and operation and management of infrastructures. Here you see photographs of the different treatment plants. In Bailín, we have one treatment plant with 2 working lines and another one that we call Bailín 2, or the Ravine treatment plant. In Sardas, we have another treatment plant that replaces, for the last 3 years, a portable treatment plant that was there before. I mean, replacing the one that was before. And all of these include runoff basins, regulation basins, and other ancillary equipment. Thanks to these treatment plants, we were able to treat the flows that you see on the graph, on the chart, that are associated to the rainfall situation that year. 2 minutes left. Another infrastructure that we exploit, manage, and operate are the laboratories in the sites. At the 4 photographs that you see on the left-hand side, these correspond to the Bailín lab. And on the right-hand side, you see a photograph of the Pirenarium, which is the reference laboratory for POPs, persistent organic pollutants. On the last year, we analyzed more than 6,500 samples. The analytical capability or capacity of the lab is a very fundamental aspect that we need to be proud of, because it is transparent. It provides a transparent and very quick response. The increase of this analysis in this chart, you can see this increase is due to the investment and the effort carried out by the government of Aragon to conduct all these research tasks in the sites. The yellow part, as you can see, is increasing every year, and this is the number of analyses per year. The other big leg, let's say, of the table is the technical assistance. Here you see different reports developed by SARGA, as well as design studies, projects according to the requirements of the government of Aragon. Apart from the design, development of these projects and reports, we always need some construction management. Here you see different photographs of works that we've been implementing from the project phase to the execution phase. As for R+D, here you see different techniques that we are carrying out with the line and the development marked by the government of Aragon. I'll finish here. All this cannot be done without the framework of coordination of health and safety and the coordination of entrepreneurial activities. You must not forget that this is a large investment and a really devotion to every novelty activity. We need to dedicate a lot of time, and it means a lot of technical challenges, every industrial or commercial activity, and we have interiorized this. As for investment, the government of Aragon is making the effort of investing at least 1.3 million euros in the development, management, exploitation, maintenance, operation tasks. The most important sections, as you can see on the chart at the right-hand side, are the treatment plant management, the lab management, and environmental follow-up or monitoring. All this that I just told you very, very quickly wouldn't be possible if without this team, multidisciplinary team that is really involved and committed. Thanks to them, we have conducted all these tasks. Here you can see all the office, the plant, and the lab team teams. Without them, nothing of this would be possible. None of this would be possible, sorry. Thank you very much. Okay, now Ana Ruiz, who is a Sarga technician, and she has been responsible for many years of the lab and the treatment plant, and she's going to speak about environmental monitoring at the Sabiñanigo site. Hello. I'm going to speak about the environmental monitoring in the spaces affected by HCH by the government of Aragon through the public company Sarga and how it is implemented. The environmental monitoring includes the surface water and groundwater quality follow-up or monitoring, the ecological status of sediments, vegetation, and animals, and the air quality monitoring in the affected spaces. The affected spaces are the Inquinosa, the Sargas, and the Bailin landfills, and the old Inquinosa factory. I'm going to start by the surface water quality. The surveillance protocol on the Gallego River defines the actions to be carried out in case of detecting HCH contamination at the Gallego River, which is sectorized in 4 different areas. The Zone 1 or Area 1 between Sabiñanigo and La Peña Reservoir. This has the name of MZ1. And 2 is MZ2 between La Peña Reservoir and the Ardisa Dam with a sampling point at the Carcavilla Central. MZ3 from the Ardisa and the Tardienta branch with another sampling position at the Gallego Canal, and the MZ4 between Ontinar Dam and Ebro River with sampling gauge or sampling taking point at the Ontinar point. And then there is the surveillance protocol at the Gallego River. The intensity of the sampling decreases as we move away from the sources. MZ0 and MZ1, the sample taking is daily, it's done daily. In MZ2, it's done twice a week. In the MZ3, it's done once per week. And in the MZ4, it's done once per month. In case of higher rainfall episodes on the Bailin landfill, which should be higher than 30 liters per square meters per day, we would increase those sample takings downstream. The threshold values, the alarm threshold values are in case we reach more than 0.5 micrograms per liter of any isomer, we would increase treatments in potabilization with activated carbon. If we increase 1 microgram per liter, we would cut off the supply. Since the implementation of the surveillance protocol, we never had to interrupt the supply of drinking water, but we have been checking the correct operation of the drinking water treatment facilities, always with values less than 0.1 micrograms per liter of any isomer. This is the photograph of an automatic sampler with an aspiration pump, which takes samples every 30 minutes. This is taken to one of the bottles, and then we analyze a full sample or a full analysis of the sample of the water collected in every one of the bottles. This is the MZ0. This is the MZ0 sampling point. Here we take the water circulating at the Bailin ravine in the area affected by the landfill, the clean water circulating by the bypass, which is upstream the Bailin landfill, and the discharges of the treatment plant of the Bailin ravine, which are discharged here. Since the implementation of the bypass, the performance of the ravine treatment plant has been optimized. more sampling points here. These are surface water sampling points. This is called RG, which is taken daily before the incorporation of the water to the water treatment plant in Sabiñanigo, and it characterizes the water before the Bailín landfill. Then we have RG04 that analyzes the water circulating. Well, it takes samples twice a week, and it analyzes the water going into the hydroelectric power plant and characterizing the outflow of water from the Sabiñanigo reservoir. Then we have RG02 taken quarterly and the RG05 taken daily. This is a scheme of the flow from the Pyrenees to the Ebro River, where the Bailín landfill, there is a series of contributions, flow contributions by the Basa River, the ravine, the urban wastewater treatment plant discharge, a series of ravines to Libana, Fundanito, and Bailín, and some flow reductions such as the Javier Relatre hydroelectric power plant diversion canal with a 95% of flow. And there is this complexity creates some uncertainty when it comes to determining what are the isomers prevailing over others. More sampling points here in the Basa River and the Aurín River. They are tributaries to the Gallego River, and they are taken monthly. Another important point in the environmental monitoring is the sampling of the little Pyrenean lakes. This has a name, a typical name here in Aragon, which is called Ibon. Ibon means a very small reservoir in the Pyrenees, very, very specific. So we have the mountain lake, they call them here, mountain lake Cuclillas or Cubillas, but they are very small lakes, really. Mountain Lake Asnos, Mountain Lake Sabocos, and Mountain Lake Urdiceto. These samples are taken at different depths to a maximum of 50 meters, and they are analyzed in terms of oxygen, temperature, and conductivity. And here we never detected any HCH. 2 minutes already. Okay, well, this is the follow-up of the groundwater or the groundwater monitoring with the follow-up or the monitoring of the contamination plumes of the three sources, the Bailín, the Sardas landfills, and the Inquinosa factory. And another environmental monitoring is the ecological status of the Gallego River. It studies the possible effects of HCH and other pollutants and contaminants, as well as the flow at the riverbed. It includes also the riparian forest quality, the river habitat index, the macrophytes index, the aquatic vegetation index, ecological quality ratio. There is a sampling of fish species in order to see the number of species, abundance, biomass, age distribution, and health status, and we determine the presence and concentration of HCH and other contaminants or isomers in water, in the sediments of the riverbeds, and in the fishes. These are 15 sampling points going from the pH upstream Viescas to P11 to Ontinar. We also sample 5 different points in the Sabiñanigo reservoir at the tail of the reservoir, Javier Javarella, and De La Peña reservoir as well. Okay, so I'm going to skip this. We also monitor the bird or wild bird status. These are the points where we installed some nests or nest boxes installed in the Bailín ravine, and we analyze both the rejected eggs and the birds that have died due to natural causes. And these years we have detected an improvement in the reproduction. Concentrations have been decreased, although HCH is still found, unfortunately. And here a colleague is going to explain the air quality monitoring network. Thank you very much.
And now Miguel Ángel Arjol, also a geologist of SARGA, will be talking about the follow-up of air quality analysis. Well, I had prepared 100 slides, but I will try to concentrate on just 15. A new matrix, the air incorporated to the follow-up by the government of Aragon and the unity of decontamination of the Linden Integral Decontamination Unit. We are in charge of sampling, but so far we have gone along a long path. The background are in Sondica, in Argalario, with the problem of Linden and its transfer to a safety cell. Measures were carried out, measurements, and they are published and accessible. But in the case of Aragon, the air quality only started to be analyzed in 2009 for this stage 2 or B of one stage A that was not efficient enough. Issues with leachates were spotted, so the idea was to build up a security cell and transfer the waste there. That was stage B or 2. So first it was about the construction of the necessary infrastructure and the transfer and restitution of soil. And in the second stage, Linden had to be transferred, and in stage 3, which is right now in draft, has not, of course, been executed. Basically, stages are 5 years each. We have learned a lot about quality of air measurement of air quality. The companies have improved in their tools. Here you can see the legislations applying limits to what is considered good or bad quality. For PMT, it was obvious, no more than 50 micrograms per cubic meter, but the authority never specified the limits. There was a semi-continuous measurement, so there was no, and there was no transfer of weight. So there was a worry about values over PM10. And you can see here the legislation, as I was saying here, Decree 1999 30 CE and Royal Decree 1073 of 2002 and State Decree 833 1975, establishing the particles, the particulates that were acceptable. In 2009, in 2014, the transfer started with all the security measures with 210,000 cubic meters excavated and mobilized, of which 63,000 cubic meters of Linden contamination. And the limits adopted there were for PM10, below 50 micrograms per cubic meters, and for suitable particles or particulates should be 300 milligrams per cubic meter. The integrated measurement adopted two different limits for two different levels. So our authority carried out a study to adopt the most appropriate positions with a dispersive model indicating prevalence of winds, the main flows. Here in this slide, you can see the windrows during the operational period. That was 180 days for the 34 measurement campaigns. And we didn't have any experience of emission particle measurements. So the model indicated with the reflection that can be seen here in the 2 points used for the measurement, one at the west and the other one at the east, of the concentration of particles during the works. Additionally, surveillance was about the situation of a tracer of particles in continuum and a predictive model, meteorological predictive model measuring wind, water, or meteorological conditions within 3 or 4 days. About measurement in the West, there were measurements of 30 micrograms per cubic meters, and in the East, 48 micrograms per cubic meters, but always Linden values, average Linden values are much below. And in the continuum measurement, they were also much lower, even below the ones used in the gravimetry measurement techniques. I still have 2 minutes just to say that from then on, and in the case of Sabiñanigo, the Aragon government knew what to do. We started a modulation of the area of the winds. The idea is to enlarge measurement area so that it is not going to be, air quality is not going to be used only in the area, but all around it. The experience was really useful to know that there should be different focuses. With the dispersive model, we saw the trajectories of the material to reach the different islands. This was a specific case to select from all the islands those receiving more or the highest volume of particulates. So from the measurement of 1 point, we are able to establish where the concentration came from and what the load that could be transferred from the focus. This dispersive model was considered to be the most efficient and has to be supported by specific equipments such as high volume and low volume collection equipments, particle meter counter laser technologies. The government of Aragon has a need to update all these equipments according to the regulation. Because the regulation has varied along the years, and we also incorporated 3 measure equipment in continuum together with tachymetry survey and real-time measurements. We can measure before we have the gravimetry values. in 5 points in Sabiñanigo and in others in Bailín, we can really measure the quality of air. And here you can see the 95 campaigns since we started. Well, as I said, I had 100 slides more. I will just show you that the values are below limits, so that is acceptable. And on soil, we have to apply regulations by 1995. Of course, if soil is contaminated or if the water is contaminated, you stop drinking water from there or eat vegetables from there, but we can't stop breathing. So we need to use efficient measurement, equipment, and policies. Thank you. And now Pilar Gonzalvo, she's a chemist from the SARGA laboratory. She will be talking about the laboratory in Sabiñanigo. Good afternoon. I would just like to show you about our trajectory and the work we've been doing. The government of Aragon started in 2009, equipping or building our laboratory in Beijing with improvement action in 2012 with some supplementary halls and rooms. In 2015, with the surveillance protocol of the River Gallego, it was decided to build a bigger laboratory with more space, better equipped, because the number of samples was increasing considerably. In 2019, the government of Aragon inaugurated the Reference Center for Persistent Organic Compounds, CCOP, and also last year, a particular room in the laboratory was dedicated to microbiology studies. The CCOP, which is the laboratory in Pyrenarium in Sabiñanigo, is made up of, as you can see here in this floor plan, 2 zones. One is a more administrative zone for offices with a meeting room, changing room, an office, and a control and electric supply room. And then the laboratory itself with 2 work lines. This white zone where the cleaner samples are treated coming from the river and the ecological studies, and the gray zone where the most contaminated samples are treated coming from the treatment plants in Bailín, Sargas, in the Bailín Ravine, and the contamination plumes, both Bailín and Sargas, and the different trials and research studies from different organizations. We also have the chromatography room isolated from the others. These facilities are very well equipped with air extraction cells because we were worried about security or safety of the workers due to the typology of the samples we work with. It was very important when manipulating these sort of samples to have these safety cells. All these glass spaces, glass separated spaces, the air inside them are filtered or pre-filtered by activated carbon filters, so that the air coming outside is already clean. Also, all the water that is being used in the laboratory area, in the wash areas, etc., go through activated carbon filters before reaching the sewage system. These facilities enabled us to enlarge our analysis capabilities. As you can see, in 2015, we analyzed around 3,500, and in 2022, we reached almost 7,000 samples. The matrices of the samples that we analyze, well, it could be, or it can be solid samples, also solid samples from ecological status studies, or sludge and soils. From the ecological status study, we get samples from animals, as was mentioned before. About the liquid matrix, it's superficial waters from the river, also wastewater, and hydrological monitoring samples. And about gas samples, we get samples for air quality studies in the form of activated carbon filters or cartridges, or crystal fiber filters too. So you see the different variety of the samples is really, really wide. The gray zone and the white zone have also compartments for the preparation, extraction, and analysis of these samples. The reception and treatment of samples area is equipped with analytical balances, screening machines, and cracking machines to separate the solids based on their granulometry, vortex, centrifuges, thermostatic baths, cryogenic baths, rotary evaporators. This went directly to the end. It's not working now. Let's just go back. Here we are. So when the samples reach our laboratory, they are in liquid form. We use liquid extraction systems or solid extractions with SPME cartridges. In the case of solid ones, we have different equipment depending on the contamination levels and the type of sample. We use different types of extraction techniques, for instance, microwave extraction, ultrasonic extraction, Soxtec, or catchers. Catchers are used mainly for vegetable and animal samples extraction. The analysis area is equipped with different equipment, such as measuring probes, burettes and stirrers, spectrophotometers for anions and cations. And the most important room is the chromatography room, with 5 chromatography equipments. 3 have mass detection, 2 with simple quadrupole. The triple quadrupole is dedicated to the cleaner samples and the samples for ecological studies. And then we have 2 gas chromatographers with FID and ECD for highly concentrated samples, the most contaminated ones, which mainly come from studies of research studies. Thanks to having this number of chromatography equipments allow us to separate the samples depending on the level of contamination and the origin, and also allow allow us to avoid stop. We work following inside patterns. We use also reference materials. We work together with other laboratories for counter-analysis and also collaborate with intercomparison circuits. With all these media, we have, as I said, increased our analysis capabilities and also increased the quality of our results, also the speed and the resources. So in the end, we reached the sensitivity and accuracy needed in order to meet requirements, for instance, of the surveillance River Gallego strategy. And you will all see everything in situ if you come to the visit on Friday. Thank you very much. And now Carlos Ayala is like a guardian angel.
All the work carried out here is carried out by people that have families, and we want them to go back home intact. And this is one of the important parts that or what we extract after all the work that we have been carrying out with the work with Lindane. And it is something to be thankful for, that the prevention, the health risk prevention law is really implemented, which is something that we thank for. And all the subcontractors are really very serious in terms of prevention, accident prevention and risk prevention, occupational risk prevention. When we were told to make a presentation, well, of course, the hair problem has nothing to do with HCH. That photo was taken when I was young. Anyway, so we normally say everything goes well, results are the ones that we get, and we never think about risk prevention until it happens. We have the obligation of fulfilling some legal requirements established to avoid accidents, but we need to apply preventive measures by law. One of the most important things that we have seen along all the years that we've been working in occupational risk prevention is that the law sometimes is difficult to be applied in such examples as the ones we see here, because we never know exactly whether we are going to have an X concentration of benzene in this or that borehole, or when we are carrying out probing test, we have free phase or not. And therefore, we always need to really protect ourselves very highly, very, very highly. And that means that the workers that are executing these activities and carrying them out should feel themselves comfortable and protected. We don't want to convey fear, but we want to convey respect and being cautiousness, really. So occupational risk prevention is considered by us integrally. We cannot separate risk assessment or having good facilities, etc. It has to be an ensemble of actions integrated for the development of all the processes and research that we are developing in the sites, from carrying out a thorough risk analysis to having emergency procedures, systems, PPEs that should be adequate to the work, the type of work that we are going to develop or carry out. We should also have specific health monitoring protocols that should be specific for the work or the tasks to be done. And of course, we need to have adequate hygiene measurements and control measurements. We need to have facilities that are using hygiene and wellness decontamination protocols. And of course, we need to train our staff accordingly. I always say that it is not the same to probe when you are building your own house than when you go to a borehole. The activities, the type of activities being carried out are probing in those cases, in those two cases, but they are totally different activities. So first we have a general aspect. We are doing some boreholes or some drilling and some probing, but we need to remember that we are facing a chemical risk and we will be affected by the presence of cancer agents that are dealt with by European directives like this directive, the 665 decree, with the and this entails the fact that we need to also create facilities that should have the proper protocols and systems in place. And of course, we need to juggle as well with the factor of uncertainty. We never know if we are going to have benzene and what amount or concentration of benzene, etc. So we need to juggle to play with all these factors. According to our experience, we see that we cannot do things normally because this situation is not normal, it's abnormal. And therefore, we had to create a system of indications of risk levels, which includes risk assessment, the whole circle, that is risk assessment, prevention measures for areas established with risks due to contamination, activities and/or operations and work protocols safe to be performed in a site which HCH contamination. This method has led us to us having certain dynamics in our behavior because we can make the protocols or we can establish protocols so that they will help us when we work in different areas with different risk levels and with even different measurements. They can be the same places, but at certain moments of the day or the month, they can have different risk levels and different control, assessment control, and the contamination can vary as well. 2 minutes, please. Oh my God, I need to skip a lot. Okay, by way of conclusion, I would say that we had many more actions like the specific risk assessment method. As we say, it is important, according to our experience, to have all the areas very well classified. When we work with Jesus, we work with ICON, with TIRSA, we need to have well-determined areas in the sense of concentrations, etc. We need to know perfectly well all the tasks that are developed, like, for example, treatment with active carbon or sludges, etc. We need to have also specific working protocols for those activities and the specific use of protection of PPEs, personal protection equipment. You see the pictures of the workers, they look like astronauts. And the first thing that a person that is going to work using those PPEs really reject those. You feel very hot, you want to go to the toilet after 15 minutes of working with those equipment. And especially if you work outside in outer areas and you work with Linden, you really need to control those PPEs. They need to be comfortable and they need to, for example, have some motor ventilation so that the worker will not have to feel that he needs to force the breathing, for example. These equipments increase, or these PPEs increase up to 500 times the effort. and they are very expensive, but they need to be the best equipments, because our workers are exposed to cancer elements, cancerogenous elements, and I would like to focus in the HAZOP. This functional risk assessment analysis is being installed by the government of Aragon, because so far we were developing our activities. They were very well characterized with probing, with testing, with treatment, with remediation equipment, and all the activities that companies can carry out, like conductivity tests, etc. But we see in the last 2 years, for example, we've been developing a lot of activities related with research, and these procedures are not well known, and these teams or these people are not, the staff are not acquainted with these types of protocols. And we therefore need to start developing with small interviews or small meetings. We need to make them think about the risks of the process itself, which is really useful not only to get to know the process in depth, but also to get to know all the risks that the process can entail. And this is helping us to determine the risks, not only the risk associated to the process, but the risks when it comes to developing this new activity that we're implementing. This is rather simple. And out of this HAZOP process, which is made up of questions that we ask, the result, the outcome is a series of corrective measures that applied to the process lead us to the fact that when we are executing our work, when we are carrying out our work, we don't have so much uncertainty as before. And from the occupational safety prevention, risk prevention point of view is really, really important. As you see here, these are the dynamic risk levels. We have established in all working areas and all activities a certain risk level, including equipment, a protocol of action, etc. These are different areas where any activity which is carried out in the old borehole, when the personnel says what type of activity needs to be conducted there, then we take our PPEs, and we have identified very clearly all the aspects and all the risks. As I said, our staff look like astronauts, but they are wearing this respiratory protection with motor ventilators, with filters that are combined for organic vapors with boiling points above 65 degrees Celsius and for particulate filtration. Again, remember that these people are facing a great uncertainty, and they are facing oncological elements, I mean, cancer promoting elements. These are examples of PPEs. I'm going to skip those slides. And we have this caravan, or this lorry, which is a mobile decontamination unit. Whichever work or task we are carrying out, this one black and white unit is totally mobile, and it allows our workers to have full hygiene. I mean, they can go to the toilet there, they can change their clothes there, they can get decontaminated there inside. Thank you very much for your attention. I'm sorry I had to cover a lot in a very short time. Okay, now we will give the floor to Mrs. Irene Navarro, who is working at the CIEMAT in the work that she's been carrying out, and she's been counseling on for a long, long time. Okay, good afternoon. Thank you very much for your presentation. I am Irene Navarro from the CIEMAT, and I'm going to present the work called Persistent Pesticides in Air from a former HCH production site in Spain. Although we have spoken about the environmental problem that we are facing here, I would like to give you some context. Sabiñanigo is a little municipality located very close to the Gallego River, and the Inquinosa factory produced linden for more or less 15 years. And the waste at that moment was buried in two different landfills or dump sites in Sardas and Bailín. And we calculate that between 30,000 and 80,000 liquid waste was dumped there, apart from the solid waste, 100 tons of linden or HCH and other chemicals. In 2007, the government of Aragon endorsed a project for the excavation of the old landfill and the transfer of the waste to a new cell with additional measures, isolating measures. In 2010, the necessary infrastructure was built, and the total of 65,000 HCH tons of waste and 342,000 tons of polluted soil were transferred to the new cell. And we have been carrying out monitoring the atmospheric conditions and the soil conditions in the area. Here you can see the geographical distribution of the area. Initially, 5 sampling points were chosen near Bailín. You see 2 points close to the old landfill, some offices close to the old landfill, and a point which is close to the new cell. We chose another point 3 kilometers away from Bailín, close to Sabiñanigo, which is the P5 point, reference point. Then the Sardas landfill, the Inquinosa factory, and 3 locations belonging to residential areas near the urban city center were included. And we work with polyurethane foams. Here in the photos, you can see the photos, these gauges and these positions of these gauges. And you can see how the decommissioning works were carried out. In Sardas, there were works for 58 sampling campaigns from February 2016 to November 2021. Before deploying the foam in the field, it is necessary, the puff, it is necessary to condition them in laboratory. Then we put them in aluminum foil, in polyethylene bags, and they are transported to the sampling points under cool conditions. After a month sampling, we extract the samples again through SOx-lead using toluene as dissolvent, and we purify through absorption chromatography using fluorosil columns. We clean up the samples through these methods, and we use high-intensity chromatographers, and this is conducted through high-quality systems implemented under the ISO and regulations or standards. Here you can see different sampling points. You see the concentrations are at nanogram by cubic meter, and these concentrations are very different to the national network of POPs, persistent organic pollutants, and these works are funded by the ministry. Oh, the speaker has interrupted herself. Well, the thing is, we find concentrations at the level of picogram per cubic meter, as you can see in another presentation that we will present tomorrow. Here you can see that the first two samplings at the decommissioning and dismantling of the old landfill and the sealing of the new one, they are totally significant, different from the other samples. If we consider the data from the third sampling, we see that for all isomers, the concentrations are statistically higher in the points that are closer to the old landfill, the P1 and P2 points. In the P1 point, the gamma HCH linden concentrations are higher than in the P2. In P1, there is a decanter collecting the DNAPL from the old landfill, and the most important isomer is the gamma HCH, which contributes to the linden contamination in air, in this point. And it could explain why linden does not decrease significantly in this point over time. For all the sampling points, we get good correlations among the different isomers, which indicates a common origin. These results indicate that the Bailin landfill is still an HCH source even after being decommissioned or dismantled. And according to the meteorological parameters, we have positive correlations that are good with temperature and with solar radiation, and a negative correlation with relative humidity. Through the Clauserus-Clapeyron equation here described, we establish a relationship between temperature and, well, the sampling temperature and the partial pressure of every one of the isomers in the samples. The study of the slope indicates division, the division between the surface and the air, indicating that the concentrations of HCH on air come from an evaporation of HCH in the surface close to the sampling points and not due to a transport from other areas or a long distance transport, not due to that. So, as for the concentration of the isomers in every one of the points after samplings and after a transition period, including the other two sampling points, we reach a period of stability where the most important, the predominant isomer is the gamma HCH, except for the 0.1 where alpha HCH is predominant and gamma HCH is predominant in the 0.1 P1. And on all the rest is from P2 to P5 is alpha HCH, the most important isomer. And in this case, the points presenting most important concentrations are the points corresponding to the SARDAS landfill P7 and the Inquinosa P8 points. The levels found in these points are statistically significantly higher than the ones found in other points. And P9 is a residential area that presents linden concentrations that are higher to the other residential areas. We also obtain good correlations for all isomers in all sampling points, which indicates again a common origin. As in Bailin, we obtain good correlations among the different meteorological parameters, and we need to say that we observe high seasonality, so the concentrations are higher in the hotter months. Since the spring 2021, in the sampling number 868, we see an increase in all isomers at the SARDAS landfill, as we will see. For all the points, respect to the contribution of every one of the isomers, for all points except P9, the main one is the gamma HCH, which correlates well with the behavior that we found in P5, which is the reference point when we study the Bailin site. As for the P9, is the gamma HCH, the lindane, the majoritarian or predominant isomer, which means that there might be a source that we still don't know of. And as we indicated from the spring 2021 in the sample number 68, we saw a significant increase, which does not make the isomer profile to vary. So gamma HCH is still predominant in this point. By way of conclusion, we want to say that concentrations obtained in this environment are higher than the ones we find in other locations in Spain. And the ones near Bailín are higher to the ones in Sardas, and both landfills, Bailín and Sardas, and the Inquinosa factory are still behaving as a source, an emission source for HCH, which allows us to define this environmental, this site as a mega HCH contamination site. The concentrations that we find when we can see some occupational exposure are under the exposure limit established by the Spanish National Institute for Safety, Health and Welfare at Work. The the gamma HCH concentrations in the Sardas points that are further to the old Bailín landfill are under the reference exposure level calculated by the California Environmental Protection Agency, the CAEPA. And the ones found in Sardas are under the reference established in the risk profile for alpha HCH within the Stockholm or under the Stockholm Convention. The study of meteorological parameters indicate that there is a high seasonality and which leads to having more contamination in the warmest months. We need to continue with monitoring, with the monitoring activities, and despite of remediation and containment measures implemented, further pollution and contamination control activities should be carried out to protect the environmental compartments and the human health. I wanted to focus my presentation on the results obtained with HCH, and this is why I was speaking about HCH so much. Thank you very much for your presentation, for your attention. Sorry, I don't know what I'm saying anymore. Sorry about that. Now, Mr. Aznar, the researcher, is going to present.
Now we will be hearing from someone from the institution in charge of the agency, the Spanish agency for the atmospheric quality study. Thank you for your introduction. I think I will be the first note focusing on Sabiñanigo, but yes, in HCH. So I am more or less in line with the spirit of the Congress. Anyway, good afternoon. As you can see here in the title of my presentation, I will talking to you about HCH concentrations between 2008-2019 from the Spanish monitoring programs on POPs. It is a very important facility where we work together, CSIC and another institution. And first of all, I have to talk about the Stockholm Convention, which will be very familiar to all or most of you. The Stockholm Convention is a large reaching or far-reaching convention that has been ratified by most of the countries in the world, but I think Australia and the US, among others, and its main goal is to study the POPs, HCH being one of them, listed in this convention in since 2009. The objective is to protect us, the human beings, and also the environment from these persistent organic pollutants, which, as you know, are toxic, are persistent in the media, in the medium are able to travel. So the convention imposes or requires the destruction of the intentional POPs, reduction as much as possible of non-intentional POPs, and also a good management of wastes with POPs, and also monitoring of levels in the environment to see that these objectives are or not being reached. Due to this obligation of monitoring, is why I am here talking to you. And Spain was one of the first countries to ratify this convention in 2004 and implemented a national level system for that. That's called the SMP POPs in English. Irene also mentioned that we work together between CISIC and CIEMAT. Here you can see the sites where we have monitoring points, 10 urban sites and 14 background sites. And we started working around 2008. Again, we see the passive monitor system. It has been used in Sabiñanigo. This is our main working tool in our network. It's very convenient because, as you know, this allows us to sample gas type contaminants or pollutants anywhere without any electricity, any power. We check this every 3 months, coincided with the different stations, different seasons, sorry, of the year. And we take these PUF discs and we take them to an equipment, which I am not going to delve into because it's rather complicated, but we always use the gas chromatography and different modalities as shown here. But I wanted to talk to you about what we do in CISIC with 5 urban sites and 7 background areas or sites. From 2008 up to now, with 55 campaigns, over 1,300 samples, over 1,300 blanks, and in the end, data on 69 analytes. I will be talking about the 3 majority isomers of HCH from 2008 to 2019. Okay. I want to show you what we consistently see, how levels in urban sites are invariably superior or higher statistically as compared to background locations. I forgot to say that these background locations are connected to the EMEP network. This is important for the 3 isomers we are studying here, alpha, beta, and gamma HCH. And this is important because linden is an insecticide, also antiparasitic. And why do we invariably find higher concentrations in urban sites? This is a question we really don't know. However, we detect this, and it's detected generally in the specialized literature. We are not really being exotic with these observations. We see how in urban locations there are a variability in levels, but the only one showing particularly lower levels is Huelva. about background areas, we find more variability with two sites, Cap de Creus and Mahon, with significantly higher levels, but mainly always it's urban sites with higher concentrations. And this is in line with what we find in the literature with national studies by the CIEMAT and also international studies both in Europe and the United States. And also as compared to the ICEMAT between urban and background locations. It is also interesting to highlight, and Irene just mentioned this at the end of her presentation, these are not really high concentration, just picograms per cubic meter. Well, if we compare this to the Sabiñanigo levels, here we find much lower levels, or if we compare it to levels detected in India, well, the levels are much higher there, of course. But in the end, we are really showing or detecting lower levels than in international studies. As for isomeric contribution, it is gamma, HCH, that's the one more present. More particularly in Iptania, we see the alpha as the majority, or the main one. We compare the different ratios between alpha and gamma, and this shows how linden is prevalent to the total contribution of HCH. We see how in cities it is even clearer the contribution of linden than the background sites. Also in most of the background sites, it's linden, the one that's mostly detected. As compared to international studies, the ratio alpha gamma is interesting to see, because very quickly informs us of the origin of the total HCH. Values below 1 are associated to the use of linden, a high proportion of the use of linden. From then up, we have really different situations. For instance, over 4, it means technical use of HCH, and even higher values mean transportation of HCH, because that is a very volatile compound that can be that can travel in the air, so to say. And again, about the difference between the 3 types of HCH, it is linden, the one that is more present, and mainly in Sabiñanigo, because you know about the situation with the insecticide, pesticide plant. Yes, 2 minutes, sure. As for seasonal variation, we don't really identify a clear seasonal variation. As I said, we always check these testers or these sensors every season, and it is statistically demonstrated that in autumn there is normally more values detected of HCH, but normally we don't really see any difference. We must keep in mind that we work with diffuse sources without direct volatility, so we don't get to see higher values with higher temperatures. But what is more important, or most important, is that we don't really witness any behavior that has changed over the 11 years of our study, particularly for the beta isomer, which is the minority, less presence, and the variation is really, really low. This gives us food to thought, particularly when HCH stopped being used. It is interesting that at the global level, there are like stable values detected. Finally, just wanted to share with you that the concentrations are really low, but consistent, very comparable to the ones found in international studies. We don't really see any clear seasonable behavior, nor over the time, but for the slow decrease in beta isomer. And this makes us think that there are still diffuse sources, mainly of gamma HCH, and mainly in cities that we haven't identified yet. This emphasizes how necessary are the monitoring studies to really identify these sources that are a bit elusive to us. We haven't been able to characterize and to work on them. And I just would like to thank you for your attention, and I hope this was interesting. We will be listening to one presentation and then we will have a short coffee break. Now, Mr. Javier Samper is a professor of the Civil Engineering Department of the University of La Coruña. We'll be talking about two-dimension model of groundwater flow and dissolved HCH transport.
I'm going to make the presentation in English. For those of you who came far away, even though the topic is regarding Aragon, I will try to make it easier for you. Y espero que el resto me entendáis. Okay, so it's a pity that we have the break after the first presentation because I have two talks. So, okay, I will make first one and then the other after the break. This has to do with the SARDAS, and both of them are related with modeling and modeling water flow. Okay, we have seen that these polluted sites or these areas affected by lindane, there are several pathways or ways for the contaminants to reach to the environment, air, and the other one is water. So this is related to that. So the first presentation will be about the flow model in the alluvial aquifer in SARDAS. The second one I will give, it's about the tracer test, and there is a third one from our group which will be delivered afterwards. And that one will be about the model of the landfill itself. So in this presentation, I will give just a brief introduction, main features of the study area, flow model, and very quickly, the contaminant transport, main conclusions, and future work. So at this stage, we are familiar with the site. Once again, here is the landfill, okay, SARDAS. Part of the landfill was disposed on top of the alluvial, and then we have here the river. Now it's a dam. It's a dam here and a reservoir. Okay, so here is you can see it more clearly. The landfill. It was very unfortunate. They did this road here because once again the part of the landfill was disposed here. So we have the landfill. So you will see more details about that in our third talk. And then we have this area here with some waste also on top of this alluvial. Okay, you can see here the reservoir. So in this presentation, I'm going to talk about the flow and the transport in this alluvial aquifer and how the pollutants that were released at the beginning from the landfill and later from here the waste here, how they move okay, towards the reservoir. Before analyzing the transport, you have to look at the flow. So now, if you want to understand the dynamics, if you want to quantify fluxes of contaminants, you have to do models, okay? Now, I like this profile, which has been presented in previous slides, but if you want to get the main ideas of how this site works, what is the flow, you have to look at it in this profile. So, okay, you see the landfill here, which lies on top of the marls. The marls are not impervious. You already have seen that the upper layer, the shallow layer, there is a few meters thick, is permeable, so actually the landfill is leaching, water is leaving out underneath the wall. More details later about that. Now here we have the waste that was put on top of the alluvial, and now here in the alluvial, okay, system, we should pay attention to the most permeable material, which is here, which is the gravels and sands. This is just a picture with a larger view. And if you want to, now, if we look at the alluvial system, then we have these gravels here, a few 3-4 meters thick. On top of that, we have silts, low permeability, the marls, which are a little bit permeable, but once you have a pollutant here, it will move towards the reservoir. Now, the reservoir is, you will see that is the type of connection that with the gravels, okay? Now, the reservoir it plays a major role in the hydrogeology of this area. Even though it's small, this reservoir has the special feature that the groundwater, the water level fluctuates twice per day. So you can see here it's almost 1 meter oscillation and every day. So the reservoir is the major boundary condition. Now, the field data, this is evidence that the hydraulic heads in the aquifer fluctuate every day due to the oscillations of the reservoir level. And another feature of this aquifer, which is very small, is the hydraulic gradient is extremely small. For us, hydrogeologists, it's almost impossible because we have quantified this gradient is 10 to the minus 4. So it's 1 centimeter in 100 meters. No way to measure that in the field, okay? So this is a challenge. Now comes the model, okay? I will try to make it easy for you to follow. We use finite elements. We are analyzing the flow in a alluvial system, which goes from here, the reservoir, to upstream this road, okay? Now, we are aware that we want to know more details just downstream the landfill, okay? So the landfill is here. Most of our interest, most of the data are in this area, okay? Now, final element grid, boundary conditions. I don't have time today to go into the details, but there is some inflows along the right boundary, the left. In the model, we account for the fact that the reservoir level changes, and so does the Gallego River, okay? So this is the river which has two branches, okay? And that also oscillates. All of that is taken into account in the model. We also account for groundwater recharge due to infiltration, okay? And the model accounts for the exchange of water from the aquifer to the reservoir. We consider a Cauchy condition, and basically this condition establishes that the flow from the reservoir to the aquifer, or the other way around, is proportional to the head difference times a coefficient, which is known conductance, and that conductance depends on parameters which are essential. One is the vertical conductivity of the silts and the silting sediments, the sediments that were deposited at the bottom of the reservoir, and also the thickness, vertical conductivity and the thickness. We have done a very detailed modeling work. I will skip the details, but the model takes into account the fact that the reservoir, the surface of the land, which is flooded by the reservoir, changes with time, though that is taken into account. And now, this is the end of the picture of the movie. Okay, this is at the end, but it took us a lot of effort, a lot of time to get to this point. What you see here is, okay, this is 3 months period modeling, and you can see the measured heads and the computed heads, and we are very confident that we are representing the flow in the system quite accurately, okay? Now, you can see, well, in this picture here, the reservoir oscillations are really different than the oscillations in the aquifer. And this is because between the gravels in the aquifer are not in direct contact with the reservoir. There is this sediments which are on top of the, which are between these gravels and the reservoir. Okay, 2 minutes. Now, nice thing from models is you get a lot of things, such as this is the velocity field. Okay, what you see here is the piezometric computed heads, direction of velocities, and this system is the most amazing systems I have ever modeled. I haven't seen anywhere a system like this. Look here, this is the same day, different times, okay, how the flow is switching, okay? The flow, groundwater flow is like this, at 8:30 in the afternoon, and 11:30 the flow changes. And this is due to the fact that the level in the reservoir goes up, and then the flow goes from the aquifer, from the reservoir into the aquifer. So the direction of the velocity changes. Okay, here you have a zoom, okay? So this is very interesting. Now, here is also the modulus of the velocity. This is, again, groundwater flows very slowly. We are talking about from 2 to 8 centimeters. This is Darcy velocity. So it changes every day, the magnitude and also the direction, okay? All of this is taken into account in the model. And okay, I will just go to the transport model. You need to have a good flow model if you want to simulate properly the transport of the contaminant. Now, we are now simulating the transport. We started with this, with what we call total dissolved HCH. We concentrate only on all the isomers of HCH, okay? And this is a model we realize is a simplified picture, but still useful. We consider the inflows from the landfill and also the sources coming from areas where there is some evidence of the presence of DNAPL. Now, for us, this result is quite promising because this is the measured plume. This is polluted. We are happy about these results, although we are aware of the limitations. The key parameter here is what is the distribution coefficient. Distribution means how much you have dissolved, HCH, and how much you have on the SORF or on the DNAPL. This is conclusions, okay? So, just to conclude, we have presented this model. Well, we can say that the model confirms the conceptual model that was previously formulated, but now we are very confident. We are very confident that we have a picture, a representation. We use all the data. There is a lot of data in this site. Many boreholes. We have the reservoir. We have the field test. We are able to represent that. This is a very, very dynamic system. A lot of oscillations and so on, okay? And we have to live with that, okay? So the transport model. We have identified which is the key parameter, is the distribution coefficient, which may depend on temperature, and we are asking the government of regional government of Aragon to do analysis of the dependence of the distribution coefficient on temperature. And we need additional data on what we think is the key barrier to prevent the pollutants to get to the reservoir is these silting sediments and the silts, okay? And we have very few data about the properties of this. So we are working, I conclude now, on incorporating local heterogeneities. After the break, I will present a tracer test which indicates that this aquifer is more heterogeneous than we thought. Transient flow, temperature dependence, and the dependence on dissolved organic matter. And I want to thank all the funding agencies, the government of Aragon, Engrisa, the Ebro River Water Authority, and University of La Coruña. Thank you for your attention. Thank you.
And now Javier Samper is going to continue explaining about a test that was carried out last year and this year in the SARDAS landfill.
So this is a tracer test which is related to the previous talk. So tracer test description, numerical model, and interpretation. Okay, let me give the motivation, but basically, as I said in the previous talk, there are great uncertainties on the groundwater flow. In SARDAS site, if you ask anyone working there, okay, what is the level here is similar there, so the flow, well, the flow, we don't know. We think the flow goes to the reservoir. Okay, we have models, and the models indicate what I just told you, that during the, most of the time, the flow is towards the reservoir, but in some, for a few hours, the flow changes. So this was an initiative from Engrisa. Let us do a field test, okay? So this was the motivation. Let's see if we are able to quantify the flow, and if possible, the direction. Quantifying the velocity is okay. Quantifying the direction of flow requires more detailed experiments. So let's see what we got, okay? So we are already familiar with this, and we decided to go to a place near the reservoir, okay? So now, this is the location selected. You can see that there is one borehole here, PS16H, okay? And several other boreholes were drilled, both in this line and this line. These were thought to be the possible flow directions, we will see later. And this is the distance between injection and observation boreholes, 4 meters, okay? Now, the idea was to, well, first of all, a dilution test was performed in this borehole, and this is a very simple test to perform. You just inject salt, and you perform electrical conductivity logs, and then from there you get a measure of the Darcy velocity. Okay, that was one test. And then the other one, and this is the most interesting, is a long-term bromide tracer test was conducted, and it lasted for almost 3 months. The tracer was injected here, and it was monitored in most of these boreholes, but especially in these two, L and J, okay? So now, these are, okay, some of the data. The dilution test indicated Darcy velocity of from 2 to 5 centimeters per day, okay? If you want to know the velocity of the water, you have to divide by porosity. And these are the long-term bromide tracer test curves. This is the curve in the injection test. This is log scale, and we see a very fast dilution. And we think this is probably related to part of the tracer probably was settled at the bottom of the borehole. Anyway, at the observation boreholes, L and J here, these are the breakthrough curves. So the tracer that was injected here appear in these two boreholes. So water is moving in the direction from here to here and to here, there, okay? But from here you can see, well, there is a peak here, and the peaks here in the other borehole are not so clear. Now, this was a joint effort. We provided support to Engrisa, which was in charge of performing the test. We did our best, and you will see what was the result, okay? But we did, I recall you that we did a model of the entire aquifer, and I think this was quite interesting to see that the model of the entire aquifer could be was useful to simulate a test which is only performed, I mean, the tracer will move a few meters, okay? So it is the same model, okay? So the same model, and then here you have a zoom of the injection borehole, and then, okay. Now, we did the predictions, we provided support for the people in charge of performing the test. And we did predictions based on our best estimates of the hydraulic conductivities, porosities, between 0.15, 0.2, and longitudinal and transverse dispersivities. Okay. The model was updated as the test was progressing. Remember, the tracer was injected end of June, and after a week, we saw some arrival, 2 weeks, more arrival, and well, we updated the model from time to time, and I will skip that. And this is after we had all the data. This is, okay, now, during the test, the reservoir level oscillated. We couldn't manage to, with the owner of the reservoir, to keep the level constant. Okay, so during the test, the reservoir oscillated, and those oscillations could affect the behavior of the tracer. But there is nothing we can do. We have to live with that. Now, here you can see the measure and the calculated heads. So we are confident about that. Now, let me show you. This is model, okay? But because you cannot measure the velocity in the field, you can measure the heads only. Well, near the injection borehole, in this element, the velocity during the 3 months, okay, here you have the modulus. The modulus, the velocity is a vector, okay, but you calculate the modulus, the magnitude, and also we calculated the orientation. During most of the time, okay, the angle is like this. So the velocity was in this direction, but during some periods, switch towards this, okay? And this is plotted here, okay? and this is amplified here. So you can see that when the, okay, let me see if the reservoir in blue, when the reservoir goes up and the level is above the level in the aquifer, and if this happens and takes place for a sufficient period of time, then the velocity, the direction of the velocity, which is here in black, then the velocity changes. And the angle changes from 170 to almost 0. 0 means it's just west to east. But this doesn't last for a long time. It's just a couple of hours, okay? Good. And then these are the, okay, we did a very extensive sensitivity analysis. These are the, okay, the breakthrough curves, symbols are measured, and the lines are calculated. The key parameter here is the porosity. So the peak of the tracer, okay, this is most sensitive to the porosity, okay? And the porosity, well, you could say, okay, porosity is simple to measure. This is not total porosity. This is kinematic porosity, the pores that are well connected, okay? So, well, at the end, we selected what we think, for the time being, is the best representation. And we are now aware that we have to improve, okay? Now, for this borehole, which got the largest concentration, symbols are the measure, the line is the computed, porosity 0.2, dispersivity longitudinal 1 meter, transverse is 0.25. Now, the current model assumes that the entire thickness of the alluvial, which is 2 meters, it's homogeneous, and we assume, and we are not sure 100%, that the tracer that we injected in the borehole mix perfectly in the entire thickness, okay? These are, actually we think that some of the deviations of the model from measured data, some of these deviations could be related to that. Now, this other borehole, well, here we don't do, okay, we don't do so well. Actually, there are some, you see, late arrivals, okay? And this is a summary, okay? Now, this is a summary of the two boreholes where we see the arrival of the tracer, the symbols and the model. At least we capture the trends, okay? And then we can be confident. Now, let me share with you this video. I will explain. This is the injection borehole. These are the observation boreholes. And this is not measured, computed, yeah? But look, if the tracer was injected here, it seems the velocity is mostly going in this way. This is the reason why we got, we got more tracer here than there. And probably if we had done a borehole here, probably we would have got larger concentrations. I don't have the mouse to put again the movie, so sorry, you only saw it once. And let me conclude. I think this test, the test that we performed, have been successful, even though we found things that we didn't expect. We are very happy. I think, well, Ingrisa is very happy. We are not so happy, but still confident. We think it was successful because we saw the tracer come into those boreholes. So this means the velocity is going in that direction. Now, the model was useful for this. Yeah, finish, yes. And let me finish that saying that there are uncertainties and we plan to do additional work. And thanks again to all the funding agencies. Thank you for your attention.
Okay, now we will give the floor to Mr. Bryce Sobral, a doctorate student working with Dr. Samper, and he is going to speak about the 3D groundwater flow and contaminant transport model of the SARDAS landfill in Huesca. I had my presentation in English, but I'm going to present in Spanish, and if some term is in English, I'm sorry about it. I'm going to present the 3D model that we made at the SARDAS landfill, and I'm going to focus on these questions that maybe were not explained enough for the importance of the model. I'm going to present the conceptual model and the flow model and the contaminant transport model. Elena, Jesus, and the rest of the speakers have described the area of study very well. The SARDAS landfill, where the CHC waste was dumped, was closed in the 90s with bentonite and perimetral walls. 2 weeks ago, I reviewed the project, and in the initial project, it was said that it penetrated up to the marls, which were considered to be waterproof. But as you have mentioned, these marls are not waterproof, and in fact, they are rather permeable. We believe that there is a leak through the frontal bentonite screen, through the surface marls, the FAD, and the perimetral walls along the dump, the ones you see on the scheme, have re-infiltrations thanks to the surface runoff and subsurface runoff and the rainfall flows here under the perimetral walls of the dump or the landfill and can go back to the landfill through the FAD. Remember that those are the fractured marls, and then go to the alluvial aquifer with the corresponding HCH contamination. The goals of the 3D groundwater flow model were to test the conceptual hydrogeological model of the landfill and quantify the inflow and the outflow of the areas, or the inflow and outflow areas, both in the landfill and as in the rock, in the nearby rock. And we wanted to test different hypotheses about the inflow and outflow areas. And we wanted to also play a little with different questions. What if we pump more? What if we construct a contaminant transport model? What if we consider different options, etc.? So the landfill perimeter is in black line, or surrounded by a black line, and the landfill perimeter is in red. And you can see the boreholes as well. We identified the main bentonite screen where there is a higher gradient and more information that requires more accuracy in the results. The model has 14 different layers, and the materials areas were defined according to the information that we had, the MDTs, the probes, the columns, etc. In the model, we define the material areas according to hydrodynamic characteristics. I'm only presenting hydraulic conductivities just upstream. The red part that you can see a little bit is very small. These are the more permeable, the less waterproof, and this has been tested in different models and in a 3D model with pumping test. We also take into account the permeability of the fats, the fractured marls, and 2 different areas with deep marls, a more surface or shallow marl layer, which is more permeable, and the deeper one, which is more waterproof. And the different conditions in the model were used using a balance model used or designed with Bruno Pisani, one of our colleagues, and we have different time functions. Here you see the runoff coming from the ravine upstream the landfill. This is the time function, and the rest of the entries of the nearby rock were considered constant, although this is under revision. but taking into account that there are drillings and sampling nearby, of course, we need to consider many more things. We will need to think how to improve this model. And here you see the re-infiltration of surface and subsurface runoff entries. Here you see the entry areas with the time function that has been calculated with a balanced model, considering the lower parts of the landfill, which is where we believe that there is more re-infiltration. The most particular area of the landfill, we believe, is the northwest corner, with evidences of puddles or waterlogging, and we believe that more leaks are taking place there. Leaking, or more volume of liquid is being re-infiltrated there. In gray, you can see monthly values in some months, but most of the sampling is daily, is made daily, and here, or done daily. And you see at the north of the front slurry wall or bentonite wall or screen, you see a drain which was built in 2008 and then, 2018, and another one built in 2022. We consider it a closed area. It's only opens when we work on it. So you see the models upstream and downstream of the slurry wall, and then you have a different corner at the northwest and southwest. Sorry, northeast and southwest, and they are S37 and S38C. You see a piezometric component, and the model that is designed in blue reproduces rather well the average levels in the probing. Maybe there are more errors in the northwest corner models, where we see gradients that are very high between this probe and another probing. There was like 4 or 5 vertical gradient. And in the ones, the surveys or the probes, sorry, not the surveys, the probes that were conducted later prove some discrepancies, so we need to reevaluate. The balance model indicates that the entry is through the northwest corner, and we believe that the surface sealing that was done in the landfill is working rather well, so there is a minimal entry of material. And under the wall, the slurry wall, the front slurry wall, we see the pumping in S37 and S38 drain, and this varies along the year. The ISO pieces show that in the most permeable areas up the front slurry wall, there is a less piezometric gradient, and the most important gradient are in the southwest and the southeast and northwest corners. And there are some high vertical hydraulic gradients. You don't see them really here, believe me. And there are some entries coming from the upstream basins and the lower part of the landfill, where we see great infiltration of water. I'm going to present the contaminant transport model, where we use the available information to define the transport parameters, especially porosity. We have a value of 0.15 for the infill and both the and 0.08 for both the surface and subsurface marls. We use the top layer longitudinal dispersivity between 4 and 2, and 0.5 is the transversal one. The balance between the dissolved HCH and the DNEPL is made through a constant distribution coefficient that does not vary with temperature. And we think it would be very interesting to incorporate temperature as one parameter to be accounted for. But now, and this could be done with the Complutense University collaboration, but we saw that the distribution coefficient is higher, the higher the the HCH concentration is. This is a simulation after 50 years, and after 46 and 50 years, in this simulation, the plume movement is very low, even for this distribution coefficient, but you can see it on the vertical axis. You can see higher concentrations at the fractured marls, the FAD, and probably you don't see it, but there is a kind of lighter blue color, meaning that there is HCH dissolved calculated in the model. The conclusions according to the models confirm the conceptual model developed before carrying out this model, and it gives us a rather good quantification of the entries, the outflow and the inflow of the aquifer between the landfill and the nearby rock. We believe that the northwest corner in the landfill is an especially sensitive area in terms of inflow, where some water is logged, or some flooding, waterlogging is taking place. And the preliminary transport model indicates that the basic flow of HCH dissolved is around 12.4 kilograms per year. This might not be an exact or accurate value, but it is along the order of magnitude of the estimations done. The magnitude is very, very similar. Nothing else. Thank you very much for your attention.
Okay, and now Javier Rodríguez-Arévalo, who is the manager of isotopic applications area in SEDEX, he will be talking about diagnosis of lindane contamination of the SARDAS landfill that was commissioned by the Ebro Confederation, the Ebro Basin Confederation. Thank you for your introduction. Good afternoon. In the next minutes, I will be presenting this work, this paper, on behalf of the two institutions belonging, both of them, to the Ecological Transition Ministry. This is the my script. First, a background and objective, then the method, and then the definition of the hydrological system of interest, and the hypothesis on the origin of the contamination of the Sabiñanigo reservoir, which is the main issue of this paper. The bad qualitative state and the alert network of HCH lindane contamination prompted this study, and also this affects the planification of the maintenance of the river. Between 2020 and 2021, this study was developed, was drafted. I'm not going into the information management, but we were asked to study the pollution episodes upstream of the Sabiñanigo Dam, which is key, and to propose what could be done in the future, which has not been done before. Now, the method is to set up a collaboration team between the Center for Studies of Applied Techniques, CETA, and the Geotechnical Laboratory, LG, of SEDEX, and review the previous studies dating back to the 1990s, and also the government of Aragon studies, together with field visits and meetings, very kindly attended by all the institutions and companies that figure at the end in the recognitions. And then we try to develop an integrated vision at different spatial and temporal scales and focus on the receiver and go back to the sources. So the receiver is the Gallego River in the Sabiñanigo Reservoir. Now, you have seen so many times these sort of charts and maps. You see a map and a graph so that you can identify again the problem. Here we have the two landfills, the two reservoirs, Sabiñanigo and Javarella. Javarella is where this alert system is located, but we were working on the Sabiñanigo reservoir. The Estación de Aforos y Calidad, that is the capacity station, was one of the main data source. We tried to detect contamination undoubtedly coming from the upstream, to separate this from what is coming to the reservoir of Javarella. So just to highlight certain key characteristics. First is the hydrometry of the reservoir with a very high variation of the water level of the reservoir, around 1 meter twice a day. And well, something that hasn't been said so far is that the reservoir is renewed 10 times a day. It is very important to keep in mind. We will have a look at the conceptual hydrogeological model, and I will be talking about water mass flows and contaminants between 2017 and 2019. Information is really important about these. Possible sources of contamination can be the SARDAS landfill, the plots at the foot of the landfill where the waste ponds are, and the Inquinosa factory. About the geological substrate, we have the marls as a low permeability substrate, then the fluvio-glacial terraces that are starting to colmate the reservoir. And you see the pictures below, which were field visits, harnessing the time of the construction of the road. That was when we could check the permeability of the marls that, due to their fractures, can also transport or allow the transport of water. About the hydrological model, I didn't really want to go into things that were already said, but these magnifying glasses are on the water coming from the reservoir, or how can contaminants detected can come into the water of the reservoir. And the landfill and the materials that has been spread over the terrace of the aquifer, of the alluvial terrace. It is important to keep in mind that this waste spread up until or down until the reservoir itself. So in the face of all this information and keeping in mind all this background, we went backwards and forwards, and some hypotheses came to our minds. These are the most important. First of all, upward percolation, leaching of waste from these plots, the foot of the SARDAS landfill, the reservoir silting sediments potentially contaminated by leachate from the SARDAS landfill, or the historical discharges or Inquinosa, leaks of the settling ponds, and all the impact of restoration, extraction, control, or surveillance actions. So evaluating these hypotheses is key in order to design remedy actions. With the treatment of our own data and the compiling of other sources' data, we analyzed this hypothesis. So the next two slides on our own treatment of information, you see here in the black line, the concentration of HCH over the 3 years. I'm not really familiar with the pointer here. So here you see peak area, also apparently here and here. These are the 3 years, 17, 18, and 19. Coinciding with this higher concentration, we see how the group of all the isomers also move accordingly. This made us think that we should find the mechanism incorporating all these isomers in the water of the reservoir. In 2018, this peak is not that apparent, and this is the key to explain how we work. We don't really just focus on the concentration values, but also mass flows. Here you see in the green line, here, and here, over the 3 years, the mass flows in grams, I think it is in grams, of the whole of the ensemble of ACH isomers going through this detection point downstream over the 3 years. In red, you see temperature values. As said before, this was one of the first times after trying to study correlation between these peaks of mass correlation or mass flows. There was more mass passing, so it is very well correlated. Those episodes with mobilization of contamination and HCH, with those moments in the year with higher temperatures in springtime and summertime. After this analysis and breaking our heads, our brains, we reached this conclusion. First is that the Sabiñanigo reservoir is currently a recipient of lindane contamination. What we see in Javarella is an addition of several things, but also in Sabiñanigo. Now, the capacity, not just the concentration values, but also capacity values, and the weekly integrated sampling of water are key. There are many surveillance networks, but it is important to keep this in mind. Now, the increase in temperature in spring and summer seems to be a determining factor in the pollution of the Sabiñanigo reservoir. And about the plausible hypothesis, we added one that was like a bit forgotten, is the subsurface leaching of waste disposed on the lower terrace of the Gallego River and percolation from the aquifer, which, well, we see that the halos of contamination towards the Gallego River point to that. So we thought that this process could be more or impacting more on the occurrence of this solution in the reservoir. About proposals for actions, first of all, advancing the evaluation of the postulated hypothesis, that many things that have not been explained. So we suggested to expand monitoring networks and to focus on the next peaks in episodes of contamination with samplers at different depths. So review the monitoring. Also, design and apply retention and confinement techniques with minimum impact, characterizing the flow of and transport of HCH in the shallowest stretch of the lower terrace, and then, as I was saying, apply minimum impact techniques. Just to analyze the last meta, so to say. Another suggestion was to add retention and confinement techniques, such as in the SARDAS field, reinforcement of the front wall with passive drainage and leachate purification. And in the aquifer and on the silts, try to be more imaginative and see if we can use reactive retention barriers, helping out biodegradation, natural biodegradation. And to ensure that decontamination techniques do not lead to contamination of other environmental compartments, like the atmosphere, for instance, or the river. And the expected results, we think it is key to optimize surveillance plans. It was key to have these surveillance plans to better integrate experimentation efforts and modeling, reduce uncertainties about the origin of contamination and hydrological behavior, prioritize future actions, limit the alert for possible affection to water users, downstream cost reduction in waste management, which is not really serious, but it keeps an alert, and increase confidence of technicians and society in remedy actions. Thank you for your attention. There is only one presentation left by David Alcalde, who is the manager of the project in Beilín for the past 10, 12 years. When he finishes, well, we are really, really late, so there will be no time for questions. So please ask your questions personally. There will be the bus waiting for us on the main door, at the main entrance for a tourist tour. And please remember to give back your headset for the interpretation system. Okay, good afternoon. As Jesus just said, this is the final presentation of the day. I will talk about the mass discharge temporal evolution in the Beilín landfill right before the its connection to the Gallego River. Our presentation will follow this structure. I will talk about the concept of mass flux and mass discharge. Many times are used indistinctively, and why mass flux matters in Beilín. What is the method we used for this estimation of mass discharge, and the results and mass balance and conclusions. So very briefly, I guess you all very well know this, but the flux of groundwater means that conductivity is affected and gradient is, so to say, the slant. Any of these two parameters, when each of them increases, water will speed up. What happens when there is a dump and it leaks and the dissolved mass is dissolved in the groundwater? In the end, it's concentration flow. So this is the contaminant mass that moves around an area. It doesn't need to be in the whole aquifer. Geology, as you all know, is not an isotroper nor homogeneous. It's just the opposite. It's just the other way around. So the discharge of mass is the equivalent of the addition of all the mass fluxes running through the different layers in the geology. After this short introduction, let's talk about why mass discharge studies matter. Attending to the concentrations and a study of a site based on concentrations, this may lead to not having a complete thorough image, a thorough picture. If we don't take into account the flow of the water moving, that could make us think that this scenario with 500 micrograms per liter of benzene in this case could seem smaller than in this other case in scenario B. But when we add both the concentration and the flow, we see that the discharge is smaller, whereas the mass discharge is higher, even the concentrations are much higher. So we will see how this was key to frame and understand the context in baleen in terms of the concentrations, which are really, really high. Now, the study of mass flow and mass discharge can be, or mass flux and mass discharge, can be used in order to see what is the most dangerous or hazardous zone, or to define a conceptual model, or to identify sites and prioritize them and treat them first, those who are more hazardous, or to monitorize long-term networks, for instance. And now let's take this to the baleen landfill, where we have been working for so many years. Baleen is here. Sabiñanigo is up here in the north. It's eastwards looking image. This was said before. Baleen is in the inverse flank of an anticlinal, where the geology is vertical. Here, geology is really ruling the picture. All the modelizations, all hypotheses, all basic measurements think about or talk about homogenic scenarios, but this is not the case. The baleen landfill is made of sandstone and siltstone layers with a peculiar distribution that affects the groundwater. So in the first media, it is a more fractured media. And as you go deeper and deeper, fractures only happen in the sandstones layers. This is a view of all the baleen site where, with the source, the demantled landfill. And here some sandstone layers. This, like the M layer, has a longer continuity that reaches the Gallego River. To make it more easy to see the groundwater flux and the implications, it depends very much. It really depends very much on the density of the layers. So water is there where fractures exist. So there might be transversal transport or flux, but near the river, the flux of water is at around 25 meters. So water can only circulate through the fractures at this depth, because the adjacent siltstones don't really feature any fractures. So a borehole that is really at 1 meter with a siltstone nearby doesn't really show any groundwater. So the studies of mass between 2015 and 2021 are exactly in the area of the discharge area. So the piezometers that are right before the Gallego River. So here you see the plume. Actually, this is M layer. If the flux of water in a normal scenario, this should be the focus, and the plume should be in this other direction, because the piezometry mimetizes geology, but in geology and the fracturation system really affects the movement and transport, even at 90-degree diversion. So the only sandstone that really has any continuity towards the river is the M layer, and in this other area we have piezometers with really high concentrations, really close to the river, just 10 meters from the river. So we really need to use both values to really understand the magnitude of the problem. This is a profile showing where there is D-nable on the deeper and shallower fractures. So the level here, the level of groundwater here is shallower, and as we get closer to the river, the groundwater is deeper, only through the fractures of the sandstones. In the discharge studies, to see what the mass is reaching the Gallego River, concentrations around of chlorobenzene. You can see the diagrams here showing the different concentrations. This pismetric at different depths to monitorize the quality, chemical quality of the water, show different average of concentrations, which are really, really high. 4,000 micrograms, 8,000 micrograms. If we compare them to the regulation reference values, we are really, really far from reaching those values. For benzene in the aquifer, it should be 20 micrograms per liter, and we are 4,000 micrograms per liter. So the values are really, really high here. Also, for surface water, reference values for the river are really low. With these concentrations, one should have goosebumps, because we are only 10 meters from the river. We must understand what it really means, what contaminant mass is really reaching the river, or at least to understand how much the aquifer is impacting the peaks detected in the river water. So there's a need to connect the groundwater flux and not just see the image or the half of the movie, or manage these sites based on just the concentrations. So for that, the mass discharge study was done right before the river. For these studies, it is important that the place, the transept, contains the whole of the plume. As you know, it's in the M layer, because these boreholes are really, really affected. In other boreholes in this area, we see there's a big difference. Well, I won't go into that much detail. The objective is to monitor the mass that reaches the river and the different isomers and benzene, etc. So we try to estimate the flux of mass flux, and to try to estimate through a mass balance how much is getting to the river. So we use these passive flux meters. They are passive samplers that can determine the concentration, and when groundwater passes through them, the pollutants are adhered to the activated carbon and retains these contaminants, and based on these we can estimate speed and the solubility coefficients. So this is just an example of our estimations. We suppose that all the fractures are hydraulically active. These show images of the rock. It is so solid that the probes can't even pass through. But for the estimation of the mass flux, we consider that all the fractures really allow for pass through of groundwater. We particularly work on areas with higher hydraulic conductivity, and we estimate flux mass for each of them. We really need to know the area in order to have the whole picture. So I'm really trying my best to finish. Anyway, M layer has 3 meters. In order to be conservative, we estimate minimum and maximum of 1 centimeter, overestimating the opening of the fractures. And here we see the results of the monitoring of minimums and maximums and their evolution over the years. We saw that 2021, at least as compared to SCH, or in terms of SCH, it increased. Before that, we need to do the balance with the information from the river to see the final, real, actual discharge into the river, which are really below regulation values. So despite these high concentrations, contribution in mass to the river is not that significant. And these are my conclusions here. Mass discharge and mass balance indicate there are no concentrations of COC in the river due to M-layer mass discharge. We also saw that intensive remedial actions related to injections in the site produce a washing out of the fractures. So there's an increase of groundwater flux and its velocity, and thus higher mass flux. And about injections, one thing is work in the middle of the plume or near the source. And mass discharge studies have been carried out during the in the natural situations of the aquifer, but when the aquifer was not under pressure of any remediation study, that was also the moment when we did, and we recommend monitoring the MD annually. And it should also be interesting to have an estimated mass discharge scenario based on conservative parameter ranges in order to relate detectable concentrations of HCH in the Gallego River. What are the conditions for that? That the width of the M layer should be wider than 3 meters, and it also should be monitored this peak stress, peak times, because levels really increase and decrease very rapidly. And that was all. Sorry for taking up too much time. Thank you. This was a pretty intense session. I hope you now have a better idea of what we have been working on in the Sabiñanigo site. Let's rest our brains. As I said, the bus is waiting for us for the tourist tour. Don't know if you know, dinner will be at a restaurant right behind the Pilar in a building in front of the Ebro. We will meet up at 8:30. So let's have a drink and have a rest. See you tomorrow.